Welcome to the UltraScale and UltraScale Plus training for native and component mode. We have a new I/O architecture with UltraScale devices, and I'm excited to show you how that works. In this quick take, we will focus on discussing the native and component mode terminology. We will discuss details around the UltraScale and UltraScale Plus architecture. And finally, we will discuss how to start designing with either native mode or component mode using this new architecture. Here's the current related documentation for UltraScale and UltraScale Plus native and component mode, which can be found on the Xilinx.com website or through the Xilinx Document Navigator. The Document Manager is useful since you can search for specific document numbers quickly to find your desired document. UG571 is the UltraScale SelectIO User's Guide. This User's Guide explains the design details about native and component mode. PG188 is the product guide for documentation on the High Speed SelectIO wizard. This document describes functionality and features for the High Speed SelectIO wizard. The High Speed SelectIO wizard is for native mode use only. It does not support component mode. Component mode is meant for migration between previous families to leverage previous designs. Here's the agenda for the quick take video. I'll give an overview of what native and component mode is. This will lead into the UltraScale I/O architecture discussion, followed by component mode and native mode details. And finally, we will discuss the High Speed SelectIO wizard, which is the main tool for native mode designs. What is component and native mode? What are these different modes? What do they mean? Component mode is a legacy support mode intended for easy device migration. Component mode can only support data rates up to 1250 megabits per second. Component mode supports primitives supported by 7 series and earlier devices with a reduced feature set. Please see UG571, which is the UltraScale SelectIO User's Guide, for more information. The User's Guide contains I/O information for both the UltraScale and UltraScale Plus architectures. Component mode can support I/O DDR, I/O SerDes, I/O delay, and I/delay control. Component mode uses global clocking, which adds noise limiting the performance. However, as a trade-off here, PLIN flexibility is better with component mode. Clock routing is different between native and component mode. Again, see UG571 for more details on component mode. So now what is native mode? Native mode is a new mode for UltraScale and UltraScale Plus devices. This is the native way to use hardware PHY to achieve the highest performance possible. The maximum performance for SelectIO in native mode is 1600 megabits per second. With native mode, there are new sets of primitives, TX-RX bitslice, tri-state bitslice, and the bitslice control, and subsets of those, which is different from previous device I/O primitives. It is important you see UG571 in the library's guide for specific details on these device primitives. Native mode also has a built-in self-calibration called BISC. The self-calibration block is a digital control and calibration block inside the bitslice control component based on a delay locked loop DLL circuit and digital delay line phase detector. The BISC controller calculates the desired tap values for the digital delay lines and keeps track of these values over voltage and temperature drift. More details can be found in UG571. Native mode is ideal for parallel source synchronous types of designs. To build any interface in native mode, the recommended method is to use the High Speed SelectIO wizard. This comes standard in our IP catalog. The next topic will cover the UltraScale family I/O architecture. Here's some background information on the UltraScale family I/O architecture. With the 7 series and previous devices, the previous bottom-up design approach was limiting. I/O logic was built from previous FPGA primitives and clocking structures. This introduced a lot of muxing, which was limiting the performance. The goal was to achieve DDR4 rates, which was very challenging with the older architecture. The phaser was introduced to help overcome those previous primitive limitations. However, additional performance was still needed. With the UltraScale I/O architecture, the goal per performance needed to achieve up to 2667 megabits per second. The architecture was redesigned from scratch up using a top-down approach. The top-down approach focused on designing an ASIC quality PHY first without compromising any signal integrity on the critical paths. These new primitives were then mapped directly to the lower level bit slices in the PHY. The two modes for the logical I/O are called native mode and component mode. Here's an example of how a previous FPGA I/O type of design might start. You have data coming in and out of the device on an I/O, which the input goes to an iSerdes deserializer. This does a 1 to 4 deserialization. To align the interface or further increase performance, an input delay element is added called iDelay. This allows for fine-tuning of the input delay for that specific signal. Next, you bring data into an input FIFO and connect this all up. For your output, you would use a serializer primitive, which is the OSerdes. For the output, you are serializing 4 to 1 in this example. You have your output delay element to fine-tune the output delay. Then you build up the rest of the interface signals. You have your strobes, DQS and DQS bar, which the phaser handles for source synchronous interfaces. This type of implementation creates much muxing that creates much compromise. With the UltraScale family of devices, the approach was top-down focused around building really great hardware first and foremost. Using a similar type of example from the last slide, here we have an I/O interface. The DDR4 solution is a complete integrated solution which the I/O is designed around. Leveraging the resources, we can use this I/O structure for a wide variety of applications. With the integrated PHY, we now have the new primitives RX-TX bitslice, TX bitslice, and RX bitslice are subsets of that RX-TX bitslice. These map very close to the hardware PHY. Now we have what we call the bitslice control that can handle automatic channel alignment for source synchronous type of designs. The bitslice control has local clock routes directly from the PLL and or RX bitslices, which allows for the higher performance of the I/Os. Here's another example of a source synchronous type of design that works well with the UltraScale native mode. Here's the layout for an HP bank in the UltraScale family. The HP banks have a total of 52 pins. There are 4 byte groups within a bank, where each byte group contains the upper and lower nibble. The upper nibble contains a single bit slice control, 5 differential capable bit slices, and 1 single-ended bit slice, which is labeled bit slice 6 in the picture to the right there. That diagram to the right shows the contents of a single byte group within a bank that contains both the upper and lower nibble. The lower nibble then contains a single bit slice control and 5 differential capable bit slices. There are no single-ended bit slices in the lower nibble. Within a bank, there are specific clock routes depending on how the I/O is configured. In native mode, the input clocks must come into a DBC or QBC pin and must be routed to the appropriate byte group or nibble in which the clocking is needed. For the inner byte clocking, this is the diagram on the right. Clocks are passed between nibbles of different byte groups depending on the inner byte clocking attributes. See UG571 again for more details on this inner byte clocking. The inner nibble clock routing is shown in the diagram on the left. The clocks can be forwarded between the upper and lower nibble depending on the clocking needs. The High Speed Wizard takes care of these inter-nibble and byte clocking rules automatically. Here, this shows how the DBC and QBC pins come into the upper and lower nibbles. Here's an example of native mode performance for a Vertex UltraScale device. Native mode has a performance from 300 to 1600 megabits per second, which is built using the High Speed SelectIO wizard. Component mode can go up to 625 megabits per second SDR and 1250 megabits per second DDR. Component mode can also operate to much lower frequencies than native mode. Moving on to component mode. The intent of component mode was to provide backward compatibility for migration and transition into the new UltraScale native mode architecture. We do support the I/O DDR, I/O SerDes, I/O delay, I delay control in a limited fashion. And again, see UG571 for more details on the limitations of those primitives. These primitives don't have the same feature set as the previous device family, so it's important you understand what the limitations are when migrating between these device families. I/O SerDes, for example, have a significant feature reduction. No more bit slip or wider range of data, oversampling. Check the user guide for more details. I/O delay and I delay control are still primitives, but again, check UG571 for all the details on that feature set. In component mode, all the clocks come from the global clocking network using BUFGs. Each UltraScale byte receives 6 global clock inputs. The muxing route these to the specific component clocks of the component primitives. The system performance here is limited to 1250 megabits per second because of this kind of clocking. To further look into the details of component mode, the maximum frequency, Fmax here, is limited because of these long global clock paths and the core noise on VCC int. This added duty cycle distortion and jitter. Data is not flapped out, adding DCD, and there is also known skew between clocks, clock div and clock B and clock div. Finally, the component mode summary. Component mode is similar to the previous device generation feature set. There is bit level support, and each primitive can be configured on a per bit basis similar to the older methodology. The I/O pin placement is flexible because of the global clock routing, and the RTL can be written independent of the physical placement of the I/O pins. The user can then lock those pins down at any time. Component mode is not 100% retargetable. Again, check UG571 for the feature set. Native mode should always be encouraged when there is any doubt on meeting system timing. Next, we have native mode. Native mode uses the new primitives, the bit slice primitives, which map directly to the High Speed PHY. The primitives are built up using the High Speed SelectIO wizard. The primitives are listed below here. This is preferred for non-memory designs that want to avoid the frequency limitations of component mode. Remember, component mode can only go up to 1250 megabits per second DDR data rate, where the native mode can go up to 1600 megabits per second DDR rate. Parallel source synchronous interfaces should use native mode even if there are no timing concerns. Native mode in general is set up well for source synchronous type of interfaces. Here is a breakdown of the RX bit slice primitive. A similar component mode equivalent would be an iSerDes plus iDelay plus a receive FIFO. The RX bit slice supports 1 to 4 or 1 to 8 deserialization. Odd data widths are not supported, as well as 1 to 2 mode. The bit slice control can also track delay over voltage and temperature to make alignment adjustments as needed on the fly. Very useful for source synchronous type of designs. Talking about the transmit slide, the TX bit slice, the component mode equivalent would be O SerDes plus an O delay. The user could also use an input FIFO as desired. Again, the serialization factors can only be 8 to 1 or 4 to 1. Bit slice control will help with adjustment of delays over voltage and temperature. TX can transmit a clock from any bit slice. Here are the native mode RX clocking details. It is required the receive clock or strobe is connected to the bit slice 0 of a nibble of a byte group for proper clock routing. This clock is fed back into the bit slice control, which is able to calibrate the clock data relationships and stores this into the register interface unit, or RIU. This calibration is maintained over voltage and temperature. There is a bit slice control per nibble, which clocks can be forwarded from the other byte groups or nibble position to the bit slice control associated with a particular nibble. This PHY is ideal for source synchronous type of applications, as there is no delay tuning needed for each data signal. For the native mode TX clocking, The master bit slice control clock is the line rate clock of the data. The bit slice control can track the delay over voltage and temperature, which makes this ideal for source synchronous type designs. The TX side is a little bit less complex than the RX side, as you can see here from the diagram. The Nibbles in native mode cannot support a true per bit independence because of the bit slice control. The nibble of the bit slice must be connected to a bit slice control. This can introduce complexity when building the design directly in HDL. The tools for building native mode designs is called the High Speed SelectIO wizard, or HSSIO for short. The HSSIO will handle all the inner nibble and inner byte rules for the user. This wizard really helps to simplify design complexity by taking care of the rules required to build an interface with native mode. The wizard currently only supports a single bank of IP. Some of the supported features include clock phase shifting, data phase shifting, data rate options with the PLL, to name a few. And last, we will talk about the High Speed SelectIO wizard. Here's the main wizard configuration page. You can select the bus direction of an RX or TX type of design. Pin planning happens in the wizard, so the user also selects the bank number. You can also set the interface speed and the PLL clock frequencies. To see a list of all the supported features, please see PG 188, which is the product guide for the High Speed SelectIO wizard. This wizard only supports a single bank configuration, so if a design needs multiple bank interface support, the user will need to generate each instance of the IP through the wizard. This is because the pin planning happens within the wizard. You cannot just simply instantiate each IP multiple times. You need to generate each IP you need for each individual bank through the wizard. In the pin selection tab, you can select any available pin within the bank and set the bus direction, signal type, single-ended or differential, and if the signal is a data or a strobe clock. The input clocks must come in on the bit slice 0 of each nibble. Here's an example of those. The pin label will have a QBC or DBC name, which are the valid clock input pins. A transmit clock can be output from any pin. Signal names can also be renamed here in the pin selection tab. The pin selection tab is pin planning per bank. This maps out to 4 byte groups, as you can see here. In the pin selection tab, you may need to scroll up and down to be able to have access to all the pins within the bank, but they are all available. In 2015.4, the pin mapping was different from the user guide mapping, as you can see here. The pin mapping is reversed. This is being fixed in the 2016.1 release, but please be aware for the 2015.4 and earlier versions. This can also be found in the master answer record for the High Speed wizard. We also provide example designs from some of our IP that will build a full interface which you can test in hardware. This high-speed wizard does include example design support for a limited set of configurations. After you configure the IP, right-click on it and select Open IP Example Design. This example design will build a loopback type of design. For example, if you had a TX type of interface, the example design will build a complementary RX type of interface to loop back to the TX signals. Please use example designs when you can. They're very helpful to understand how components are being connected and used. And that was all the material I had for this presentation. Again, check the documentation for more detailed information. UG 571 is going to be a good resource for this. Thanks for watching.